Okay, so for our meeting, my suggestion, I was thinking that I don't do the presentation. Instead, I don't. Could you like ask me some questions, some simple questions that the community like may ask, and then I can try to answer them, and then you can comment.
You want me to ask questions? Well, I'm not. I didn't write set of questions right now. Questions will appear while listening to your presentation.
So I present, and then you can ask me questions if you have any.
Yes, yes, correct.
All right, since we only got like 45 minutes and I have to leave at 3, I'm just going to give an abbreviated talk.
Yeah, sure,
All right,
sure. Please do.
okay. So, excited states in one dimensional thermoelectric materials. You can see my screen, right?
Yes.
All right. So, why is charge transfer important? First, I'm just going to give a brief description of what charge transfer is. So, in this panel right here, you have an electron that's excited by a phonon. It absorbs that energy, then it comes back to fill that electron hole, and then it fills that hole. So charge transfer is essentially a movement of electrons. So charge transfer is a very important phenomenon because it occurs in semiconductor application, and semiconductors are used in everything. And also, it presents on exciting developments in the theoretical aspect. For instance, non-adiabatic dynamics, which describes nucleus electron interactions, can explain a charge transfer. So it's very important in that aspect as well. Um, so I'm studying the thermoelectric effect. But first, I want to contrast that with the photovoltaic effect. So here you have sunlight, and it's emitting photons, and it's exciting all these electrons. So you have an electron flow from an area of excess electrons uh, towards an electron hole, and then you have your N-type and P-type materials, and then there's a junction connecting them. So this sunlight is inducing electron flow, electron transfer, and that is powering this electrical circuit and this light bulb.
Kevin,
Yeah.
why does one need both P-type and N-type semiconductors at the same in the same system?
Okay. So and N-type is your electron donor. So it's basically the one that's giving the electron, and your P-type is your is the material that's accepting the electron the N-type is giving. So the electron flows from the N-type, which is donating the electron, to the P-type, which is accepting the electron. So you need both N-types and P-types because you need an electron donor and acceptor respectively.
Okay, good. Please keep going.
All right. So what I'm studying for my thesis is this the thermoelectric effect here. So you have your hot side and your cold side here. Uh, on one side you have an excess of the electrons or electron holes, and then on the other side you have your cold side. So charge is basically transferring from your hot side to your cold side, and on the hot side, because the temperature is much greater on one end and the other, some electrons have greater kinetic energy than the other, so the electrons or holes with greater kinetic energy move towards the cold side faster, and then when enough of them gather together, uh, they produce electrostatic repulsion that pushes the electrons or holes of lower kinetic energy on the other side. So you have charge on one side and charge on the other. All right. So when you have two charges on one side, you have a dipole, so you have a voltage between them, and that induces a current. And then so that's panel A. On panel B here, you have the thermoelectric effect, and that's being used to induce a voltage across a resistor.
Kevin, may I ask?
Yeah.
Would it be correct to say that heat source temperature gradient replaces a photon by making analogy to photovoltaics? So the source, the reason for charges to move is the temperature gradient.
Right.
While in the photovoltaics, reason for charges to move is quanta photons.
Correct.
Okay, yes, please keep going.
All right. So for my study, I studied lead telluride nanowires. So you might be asking why we're studying nanowires as opposed to thin films. Well, it turns out that their electronic properties are easier to modify, monitor, and control. So it's easier to add impurities or remove atoms from nanowires than it is in thin films. All right, and they've been widely researched due to their potential as a thermoelectric material. So their conventional band gap is around 1 to 1 and 1.5 electron volt. The conventional band gap for regular semiconductors. However, the lead telluride band gap is around 0.32 electron volts at 300 Kelvin. So that's really, really good as opposed to regular band gap. However, many challenges remain. It's very hard to apply this material to the real world, and also if you just take any regular lead telluride nanowire, their charge transfer rates are very low. So what scientists and researchers are doing right now is studying doped lead telluride nanowires to see if it modifies its electronic properties, namely if it increases the charge transfer rates. All right.
Mm-hmm.
All right. So quick uh, quick detour into the doping process. So panel A is your regular undoped material. So the valence band and conduction band remains unchanged. Sodium doped and iodine doped. For panels B, B, and C. For panel B, the valence band is empty, so electron is taken out of the valence band. And then for panel C, the conduction band is filled, so the conduction band, so an electron is being added to the conduction band. So here in panel B, you have a photon exciting electron in the valence band, and then that electron travels to the conduction band of iodine. All right, so that's how the doping process works. Okay, so here's a model of the structure I studied.
Kevin, in your panel D, you do have iodine doped conduction band top occupied, and the bottom, the top of the valence band in sodium empty, and bottom of the conduction band iodine is filled. But this is only for excited state. You may want to mention that in the ground state, the p and n doped states exchange the occupations. Ask me later if I make a note on this, but ask me later about it if needed.
All right. So you're making notes for everything I talked about today, and then you'll email them to me.
Yes.
Okay. All right. So here's my so, my doped lead telluride nanowire that I'm studying. The length of a unit cell is approximately 110 angstroms. Here's my iodine and my sodium. I have a cubic structure. There's approximately 300 atoms on there. So lead and telluride occur in the 1-to-1 ratio. That means for every lead, there's a telluride. So lead has uh, lead has originally has 2 extra electrons in its valence band, and telluride needs 2 electrons in its valence band uh, to become happy. So what happens is that lead donates 2 electrons to telluride, and together they form a compound. All right, uh, and then iodine needs an electron to fill its valence band, and then sodium has 1 extra electron in its valence band. So sodium gives its extra electron to iodine. All right. So sodium replaces lead because they both have extra electrons, and then iodine replaces telluride because they both have electron holes in their outermost band.
Kevin?
Yeah.
What is the distance between two nearest lead and telluride atoms?
The distance between 2 lead and telluride atoms.
If you don't right now, it's okay, but please check it and provide it on this slide, because committee members will be likely will be curious about it.
Okay. All right. So before I get into the results, um, here here are the analytical methods I use to study my system. So I use density functional theory uh, to obtain my position in energy eigenvalues right here. Um, so an important thing to note is that my potential here depends on the charge density right here. This charge density right here is just a superposition of every orbital I have from orbital I to my HOMO. And then a quick note, I get the positions of my ions from molecular dynamics. And then I have my eigenvalues, then I use non-adiabatic couplings to determine how my position and energy eigenvalues change in time. Okay, and then after that, I use this transition rates equation right here to figure out the rate of time my electrons move from one orbital to another. And then after computing all this, I use my density matrix dynamics, this equation right here, to determine how my charge density changes with time. One quick note, this charge density right here is dependent on time. This is independent on time, just to make a quick note on that. So I'm calculating the commutator between my Hamiltonian and my time-dependent charge density. And here I'm using the transition rates from here. Okay,
Kevin, can you go to slide 8?
this one?
Slide 8. You're not sharing your slides. I'm just going through the file. So in slide number 8, methods, I want to ask, how does temperature affects Newton's equation of motion, molecular dynamics?
Give me a second. Okay, temperature affects these equations or molecular dynamics because molecular dynamics essentially calculates uh, the positions and velocities of uh, of each ion that I have. All right. So what I'm doing in the study is looking at my system at the different temperatures. All right. So we know that at higher temperatures, um, there's going my ion is going to have a lot more kinetic energy. So the velocity is going to be higher at higher temperatures, and there's going to be a lot more position fluctuation for my ions.
Excellent, excellent. Thank you. It would be great to add a movie of molecular dynamics.
All right.
Okay, please keep going.
Okay, so on slide 9, I tell you how I get my observables. So here I'm showing how my energy changes with time, and I'm simply adding all my orbital energies from uh, from Nemo to however much I have. All right, and then in the next line, I'm calculating my relaxation rates for my electron and my hole. All right, so my relaxation rates is simply how my expectation values for my electron energy and hole change with time. But how, even though that's technically how I calculate that, on the next slide.
Wait. Please wait. Um, in your thesis, I was asking you to make to fix connection between Greek epsilon and uppercase E for the energy. Did you fix it? Did you found this connection? Because right here in the slides, I still see this ambiguity.
Uh, yeah, I fixed it in my thesis, but I forgot to fix it here on the slides.
Okay. Yeah, please.
I'll definitely have it fixed by tomorrow.
Okay.
All right, and then on slide 10, I have my band gap law. So the primary purpose of the study is to see how well my relaxation rates follow the band gap law. So for here, my relaxation rates is constant times e to the negative alpha delta E, where delta E is the energy difference between my initial and final states. Right.
Mm-hmm.
Now on slide 11, we get into the actual results. So on panel A, I have my undoped nanowire, and then on panel B, I have my doped nanowire. So one important thing to note here is that on panel D, you see two states A prime and A on there, and then um, you see state C on the conduction band. Those three states I just mentioned were were added by the doping process. So that's a very important thing to know. Also notice that the area uh, for my valence band and conduction band in panel B is greater than the respective areas for panel A. So what this means is that uh, there's more states available per an energy interval. All right, and then what that in turn means is that there's much more many more states available for doping, and that is correlated with the higher measure of charge transfer. So what this so what these results suggest is that this doping process has definitely uh, improved the charge transfer mechanism for the lead telluride nanowire. Any questions about that?
No, no, no.
Okay, and then here you have my absorption spectra for.
Oh, Kevin, I got question for slide 11.
Okay.
The orbitals of your model are provided in slide 15.
Right.
Check if orbitals would be more reasonable right after the density of states. Maybe not. I'm not telling immediately move them here, but I have ambiguity. For some, when you are talking about orbitals, about density of states, maybe it would be It could be reasonable to show like this orbital is responsible for that peak and this orbital for that peak.
All right, got it.
Uh-huh.
So you're saying move a slide 15 before my density of states?
After density of states, between make it number 12.
Okay.
And it is optional. Please double think about making this move. If you decide not to move, then make an announcement. Orbitals illustrating the peaks in the density of states will be illustrated a few slides later.
All right. Okay, so on slide 12, we have my absorption spectra for panel A and panel B, my undoped and doped nanowire respectively. All right. Okay, important thing to note is number one for panel B and one prime in panel A. They are both stored due to my charge transfer excitation. Um, so this is expected because the electron is transitioning between two di- different orbitals with different spatial localizations, and then yeah, that's it for my for slide. What is it? 12.
Mm-hmm.
Next slide.
Mm-hmm. Kevin, I come again to the conclusion that before you are showing current slide 13, it would be really great to show molecular dynamics trajectory as a movie.
Okay.
And I think you know how to do it. We were doing it in the class, and you can generate a couple of movies.
All right. So here we got how my Konchab orbital energies are fluctuating with time, and this is at temperature 1000 Kelvin. So, so here at time zero, we see that the band gap is approximately 1 electron volt, and then we see that the band gap essentially closes with time. All right, and this is because that the energies uh, all of each orbital are dependent on the ion's positions, which is essentially dependent on time. All right, so that's the reason for this phenomenon. Any questions about this slide?
Not right now. Keep going.
Okay, and then on slide 14, we have my red field tensors. So here I'm showing the red field tensors at each temperature. So on the x and y axis, you have my occupied and unoccupied orbitals, and then on the z axis, you have my transition rates, which is how long it takes for an electron to go from orbital I to orbital J. So here we see that at lower temperatures, the transition rates are essentially negligible, and then on higher temperatures, the transition rates uh, increase considerably. All right, and then another thing to note is that transition rates near the band gap are close to zero for initial temperatures, but at higher temperatures, um, they also increase considerably. So that's another important thing to note. Slide 15.
Okay.
Here we have all the orbitals I considered for this study. So the important thing to note is that
Kevin, can I interrupt and ask?
Yeah.
Right now, you are expanding, artificially expanding width of each nanowire, and you are probably doing it for artistic purposes to fill all available space. Please do not do it. Make the if one looks on a simple element in this nanowires, they should look cubical. Right now, one can see that each nanowire is composed of these little squares, and the squares are expanded in x dimension, right?
Mm-hmm.
This creates a deceptive impression that your nanowire is not cubic. These little squares should look cubic, as it appears in the when you do orbitals.
So what are you saying? So you're saying for this figure that I should make each the width of smaller?
Yes, I did try to fix it immediately as I can in your slides, and I will send it to you. You'll see what I did.
Okay. I will make a note of that.
Uh-huh.
All right.
Please keep explaining.
Got it. So here I show all the orbitals considered for my study. What's important to note here is that all my HO orbitals are localized around my sodium dopants, and all my unoccupied orbitals are localized around my iodine dopants. So that's just an important finding here. Next slide.
Just a second.
Yeah.
Yes.
Do you have any questions, or can I
No.
go on?
Keep explaining.
All right. So on slide 16, um, here we have another graph. So this shows uh, how my probability density is changing with atomic distance and or orbital energy. So you see here that the probability density is greatest on my conduction band on the upper right hand corner, right? And the probability density is lowest near my valence band.
Okay.
All right. Next,
No,
next slide.
wait. Please wait. I have a question. It is not for this slide. It is general for your presentation. So, how many densities? How many different like the word density and the symbol rho is used for several concepts. So it is used for um, density of electrons, right?
Mm-hmm.
It is used, which is three-dimensional. It is used for one-dimensional density that you are showing here, rho sub I of z. Then you do have density operator in in the Redfield equation. Then you do have matrix elements of the density operator, which are density metrics. Um, matrix matrix element, and then you have density of states in your figures, and plus you do have density of final states um, in your Fermi golden rule. So total, you have one, two, three, four, five, six, six concepts, each of which is called density, and most of them labeled by symbol rho. Um, if some of the committee members or audience will listen for a talk for the first time, like if some of the committee members will not read your thesis or will read it not carefully, there could be ambiguity. You may think of preparing special slide with explaining all these six concepts using the same symbol and same word, and maybe keep it under after the conclusions, just if someone asks. Because I anticipate that some of the in the audience can be confused with word density and symbol rho used too frequent, and you may want to have an answer to resolve this ambiguity.
All right.
Okay, please keep going.
Okay, so slide 17.
Okay.
So here I'm showing how my energy expectation values are changing with time. You can see at lower temperatures, especially the 300 Kelvin, there's hardly any change. However, at higher temperatures, there's a sizable difference. We see that relaxation is occurring quicker and at earlier times, and we can see that the magnitude increases at uh, higher temperatures.
Mhm.
All right. Next slide.
Please wait. If you would suspect an error here, I believe that there are no errors. But if you want to be super critical to yourself, um, which error may potentially be here? Which aspect of this calculation you would be interested to recheck, double check, and make sure that is there any suspicion inside yourself? And you do not need to tell it to audience, but be ready and think about of it. Like which aspect of this calculation is most strange and suspicious for you?
Would give me a quick second.
Uh-huh.
Honestly, I am unsure.
Okay, please develop your own opinion. For me personally, I'm not telling that something is wrong, but if I'm looking on the column with 300, then yellow and blue stripes always finish at some. They are not coinciding at the end of electronic dynamics. But if I look at any other trajectory at higher temperatures, yellow and blue stripes come much closer to each other, showing that the gap is zero.
Okay.
Is it truly so, or it is an artifact? If I would if I would redo this calculation myself, I would double check it. Although I think everything is normal, but it's healthy to have a suspicion at each stage.
Okay.
Okay, please keep going.
Okay. So here on slide 18, we see how my position expectation values change with time. So we see here one important aspect to note is that all my charge transfer is localized around my iodine dopants, which are on the top of my nanowire. That's expected since iodine is the recipient atom and sodium is the donor atom. We expect the majority of charge transfer to be localized around iodine. All right, and another thing to note is that at higher temperatures, the magnitude of charge transfer substantially increases. So, for instance, at 300 Kelvin, if you look at the top radiation, the magnitude of charge transfer is very small, but at higher temperatures, it substantially increases. All right. So
Mm-hmm.
those are the most important findings to note here. And then on slide 19, I notice how my relaxation rates are changing with energy. All right, so on the y-axis, I take the natural log of the relaxation rates of my electron and my hole respectively, and on the x-axis, I have my change in energy. So then on panel A, I look at my electron relaxation rates. It looks like there's some moderate correlation here. And then on panel B, which is my whole relaxation rates, I notice little to no correlation there with the band gap law.
Question.
Yeah.
In general, without much details, how does rate of relaxation changes with temperature?
I'm going to get to that on my next slide.
But can you tell it right here? I understand that you will tell it on the next slide.
How does my relaxation rate change with temperature?
Yes.
Um, the rate of change with respect to temperature is independent of orbital transition. So whenever
Kevin, wait. This is fine. This is tiny detail, but in very general for general audience. Would it be correct to say that if temperature increases, that the rate will increase as well?
yeah,
Okay, so
a very general way of putting it.
you can focus attention of the audience on this fact right here in this image. For example, if you look on the panel A, um, dark blue dots, lower data set,
Mm-hmm.
and then if temperature increases, all then orange circles are higher, and then yellow are higher, and so there are some fine details, but generally, if temperature increases, the rate increases as well.
All right.
And this is not a discovery, but it is a sanity check that it is very it agrees with intuitive expectations.
All right, got it.
Okay, please keep going.
And then on slide 20,
Uh-huh.
I see how my relaxation rates increase with the temperature. So we see for both my electron and my hole, the graphs essentially overlap for each orbital transition I'm studying. And what that tells me is the rate of change with respect to temperature is is the same for each orbital transition, and by the shapes of the graphs, uh, I suspect that uh, we have that this is a Boltzmann distribution. So if I go back to my earlier slide, which explains the band gap law, from there I can qualitatively determine that my alpha in the band gap law is equal to 1 over the Boltzmann constant times temperature, because these graphs have the shape of a Boltzmann distribution.
Okay. May I ask?
Yeah, sure.
So you are using Microsoft Excel, and it does write you little equations as an inset in your figures.
Mm-hmm.
Would it be, and it uses X and Y. Would it be possible to rewrite these equations in terms of physical observables, or at least explicitly write what is X, what is Y? I understand that smart reader would understand that X is equals temperature, and Y equals log of the rate. But it would be better to write it explicitly, or rewrite the equation in the form like ln of rate equals whatever you get 3.2 of logarithm of temperature minus another constant, because in converting this x and y in temperature and logarithm of rate is a big headache for audience, and the goal of any presenter is to make it easily digestible.
Okay, so just writing an equation back saying that the natural log of my ln of ke is equal to ln of t times a constant plus another constant. That's what I should be saying.
Yes, please. Well, I'm not giving exact recipe, but try to make it digestible. When you will be going through slides quickly, no one in the audience will be able to quickly convert your X and Y into the actual physical observables that you keep in mind.
All right.
Okay, keep going.
And then finally, we can conclude that doping improves the nanowire's charge transfer. The band gap is inversely proportional to the temperature. One quick thing to note is that in the future, if researchers want to improve on my study, they should look at transitions between orbital superpositions. If they do that, they'll most likely find that there's no orbital localization there, right? And then we find here that the band gap law only moderately applies to electrons at higher temperatures. There's limited applicability to by electron holes. And then finally, we note that my electron and that my electron hole relaxation rates are independent of orbital transitions when you're looking at how they change with temperature, and that they follow a Boltzmann distribution. So essentially, my research is impactful for industry because if we show that the band gap law has at least some applicability to my relaxation rates, then researchers can compute the relaxation rates quickly using this band gap law as opposed to time-consuming experiments. And yeah, that's it.
Okay, excellent. I think you need to connect to another meeting at 3, as I understand.
Yeah.
Okay, I have recorded. I did try to record our meeting, and I was writing notes. So I will send, and you'll see my questions.
All right. One last question. So, do you have any like papers or textbooks that you recommend?
Kevin, you are asking the wrong question right now. You need to go into Web of Science and find who was publishing on these subjects. There is no single source that answers possible questions. It is a state of the art that we are not studying subject that is available in textbook. You are doing frontier research that no one except you in the world knows all details. Therefore, you collect little pieces of information from here and there. It is a standard situation in science. So there is no single source.
All right, got it. So what I'm getting is that there's always going to be a bit of uncertainty involved.
Absolutely, yes.
All right, so you're saying the best thing I can do is I can just maximize my chances by like reading papers from Web of Science or other sources, I'm guessing.
Right now, well, it would be reasonable to find few more papers for DFT computations of lead telluride, but in remaining time, there is no time for systematic studies. There is time for your personal critical thinking about your work and about what is good, what is bad, and try to think that you are a committee member and you want to design a tricky question to this work, to this candidate. Try to be creative. Design questions and then design answers to them.
All right, I got it. So I guess I'll see you tomorrow at 5 then, right?
Yes. And please, please send updated slides as soon as they are ready.
Got it. Take care.
Yeah, thanks. Bye now.